methods for studying stable anions that are unbound in the Hartree-Fock approximation.
Okay, so I also want to thank the organizers. It's been a great set of talks so far, and it's been really great meeting a lot of folks that I knew from a long time ago, but for whatever reason, we haven't overlapped in meetings recently. Okay, so this is just a picture of an electron bound to a water-45 cluster. As some of you may know, much of the work in the group in recent years has been collaboration with Mark Johnson studying the nature of excess electrons in water and other systems. The first part of the talk will actually focus on this, and I'm going to show that some of the things we learned carry over to molecules like C60. But the first thing I want to say about the water clusters, if you have a water, depending upon the arrangement, they can have a big dipole, and the electron is bound in the dipole field. Or they can be arranged so there's no net dipole, and you can get these cavity species where the Hartree-Fock may not even bind the excess electron. Okay, so this is a picture of the group. It's a few years back. Some of the work I'll be describing has been carried out with Thomas Sommerfeld, whose name has been mentioned before. He visits our group every year, and we've benefited from that immensely. Mike Falsetta, who's at a small undergraduate school north of us, Grove City College, and Mark Johnson, with whom we've done a lot of collaborative work. Last night I inserted a couple slides just that weren't going to be part of the talk, but based on things I heard in talks yesterday. One of the talks yesterday was talking about water clusters and anions. And I'm just showing here some work that Mark Johnson and I did. So the experiments are obviously Mark. We just did some theory to aid in this. But showing with clever experiments, you can do some pretty phenomenal things nowadays. So what Mark has done is he's made the negative ion of water 6-. That's shown right here. In fact, all the waters are pointing OHs in the same direction. So this is a dipole-bound ion. This is known well characterized vibrationally. And then he puts on the back of this a CO2. So even though it is exothermic for the electron to go onto the CO2, he can prepare this where the electron is on the water cluster. He then vibrationally excites one of the water, either the bend or the OH stretch, or he excites the asymmetric stretch of the CO2, and then that promotes the reaction. That goes on to make CO2-. So he approached us saying, so that means the barrier has to be really small if you can just put energy in the bending degree of freedom and promote the reaction. So he asked us to study this. We did this with ab initio molecular dynamics. There are many, many pathways, but every pathway has the same event in common. And I'm showing you one of the pathways here. So the electron is mostly on the water. 15 picoseconds later, it's mostly on the water. Begins to delocalize in this trajectory at 17 picoseconds. But you notice what happened. One of the waters made a hydrogen bond to the CO2. Turns out if you work out the thermochemistry, even with the bending, it's not favorable for the electron to go to the CO2 unless it's engaged in hydrogen bondings. That hydrogen bond makes the CO2 a better electron acceptor. And that's the trigger for this process. And then it goes on and totally localizes over into the CO2. So this is our joint DOE grant with Mark and myself has really moved from just studying water to studying actually CO2 reduction. And we can now do this in these mass spectroscopically isolated clusters. The other thing is another area of research I'm very, very interested in. It's the nature of excess electrons at interfaces. And this is in collaboration with Havoya Petek, a colleague in my physics department at Pitt. This is a TiO2 surface. It has 1 or 2 layers of water on top of that. You can photoexcite the TiO2. An electron jumps from the TiO2, goes to the water surface, stays there about 50 femtoseconds, and then recombines. So, but if there were molecules like CO2 there, competing with that recombination would be reduction of the CO2. I can tell you that we don't have theoretical tools that treat these resonant type states on these periodic systems. We heard yesterday that where we stand in terms of small molecules. We certainly don't have the tools to go address these condensed phase or interfacial problems. Okay, so just sort of a background, and this is hardly needed for this evidence. I'm going to break negative ions into different types. There are those who are unbound or temporary, and we certainly heard about temporary anions in part in the DNA work that Tom talked about, and that's a long-term interest in my group. And then there are the bound anions, which we've heard a lot about. C6H certainly be an example. But from a theoretical point of view, you can break the bound anions into two groups. There are those that the Hartree-Fock binds, and you can use your standard computational chemistry methods. And there are those where Hartree-Fock doesn't bind, and that means you can't go do perturbation theory, or even coupled cluster probably is not going to be applicable. So those are the ones I want to focus on there. So these share some of the characteristics in terms of theoretical treatment that resonances, temporary anion resonances present. And I'm going to start off with a model system that shows this behavior. So this is 4 water molecules arranged so there's no net dipole. In fact, this is not going to be the arrangement of water 4- seen experimentally. This is just a model. And we can vary the distance between this dimer and that dimer. Okay? So that's going to be a model system, and we'll calculate the electron binding energy of this. So a sort of a picture, a cartoon way of thinking about this is the electron binding is going to have a contribution due to the electrostatics in the exchange. Clearly, the electrostatics is very favorable in this arrangement. There's a confinement component. Now, here, of course, the electron density can spill out, but when we go to these 3-dimensional clusters, this confinement component is very important. So that's where the uncertainty principle comes in. So in the Hartree-Fock, those are essentially the terms that you're counting. And then there's a dispersion type effect. I have a whole talk talking about dispersion in these. In this community, this might be called polarization. But it turns out if you excite this weakly bound electron and you excite one of the electrons in the water, that gives a correlation dispersion type interaction. That's obviously missing in the Hartree-Fock, and that's what's going to tilt the balance in these. I probably won't go into all of these methods. Anna will be familiar with every one of these. Some of them, I think, haven't made their way into the physics community. So MP2 coupled cluster, there are different variations of coupled cluster. I'm going to show results using equation of motion coupled cluster. There are 2 variations of this. Anyone's interested, if there's time in the answer period or during the break, I can go into the theory here. But one of the advantages of these equation of motion coupled cluster methods is they don't depend on the validity of the Hartree-Fock wave function. Another approach that we've used that doesn't depend on the validity of Hartree-Fock is just a second-order Green's function. Many groups have implemented this. We collaborated with Sederbaum's group on this, but it's essentially a second-order approximation to the self-energy, which means you're summing certain interactions to infinite order. There are 2 versions of this, and this is going to turn out to be important. In the complete implementation, the self-energy has off-diagonal terms. That's what allows the orbitals to adjust to the correlation effects, and that's going to be one of the takeaway messages. That's absolutely crucial. If you do a diagonal implementation, the orbitals don't adjust to the correlation, and this diagonal Green's function approach will not bind the electron in these problem cases. And then there are sort of new methods developed in the quantum chemistry community that are also successful at binding these. One is orbital optimized MP2, but this is an MP2 expression where you actually re-optimize the orbitals in the presence of the correlation. You can do that in a coupled cluster treatment. And then finally, we'll take a look at a Bruckner orbital treatment. So for those who aren't familiar with this, you're essentially saying when you do Bruckner orbitals, those are the orbitals in a single slated determinant that would have the maximum overlap with the true wave function if you had it. The other way of wording it is it's perturbation. It's a treatment where you've eliminated single excitations to all orders. But these methods in blue all allow orbitals to relax due to correlation effects. Okay, so let's take a look at some electron binding energies for the system. Here's the Koopman's theorem, so that's just the static exchange. So at long range, in a very, very big basis set, the electron is bound Koopman's theorem, but about 4.2 angstrom, it ceases to bind. Okay, that's due to the confinement effect. Hartree-Fock isn't doing much different. If you do the equation of motion methods, I'm showing both equation of motion methods, you get this curve here. The EOM coupled cluster includes higher order correlation effects than EOM MP2, but they're both given essentially the same results. And then when you take traditional quantum chemistry methods, such as MP2 and coupled cluster, they're binding, I mean MP2 is clearly off, it's missing correlation. They're binding right up to the point where Hartree-Fock fails, and then they fall apart. Okay, so you need methods that don't depend on the validity of Hartree-Fock to get over into this region right here. I meant to pull this out last night, but it's still in there, so I'll just mention it. If you take a small basis set, so I should point out what's happening on the slides I showed earlier, and I'll show pictures of this in a moment. In a large basis set, when you do the Hartree-Fock on the neutral, the lowest empty orbital is an approximation to the continuum. And the methods that don't redefine the orbitals in the presence of electron correlation can't recover from the fact that the zeroth order wave function is occupying a continuum. If you actually tackled this problem with a not very flexible basis set, then the continuum has sort of been pushed up above. Here's the result. So Koopman's theorem and Hartree-Fock are not even binding. But these orbitals now, the singly occupied orbital is localized in the region of the molecule. It doesn't have a lot of continuum component. So now when you do any of the methods, including traditional quantum chemistry methods, you get binding over a small region. But this is not giving a binding energy curve that's in good agreement with the results obtained with large basis sets. So you can sometimes trick traditional quantum chemistry methods by just having a basis set that excludes large continuum components. Okay, so this is showing the Hartree-Fock singly occupied orbital and the natural orbital from the equation of motion. For those who are familiar, this natural orbital, this is the singly occupied orbital, from the equation of motion is very, very similar to the Dyson orbital that this excess electron would occupy in a Green's function. I don't have the plot here, but separately we plotted the Dyson orbitals and the natural orbital. So you can see at all distances, remember 4.2 is where the electron no longer binds Hartree-Fock. Even when we push in shorter than that, the natural orbital has significant weight in the molecular region, whereas the Hartree-Fock is just going on and on and on. It's an approximation to the continuum. Only when we get a long distance does the Hartree-Fock begin to look like the natural orbital. Okay, I'm not going to give you numbers or curves for this, but the other point is these other methods, the second order Green's function method, the orbital optimized MP2, the orbital optimized coupled cluster, and even the Bruckner method, all give electron binding over the whole range of distances. And again, that's because these methods can reoptimize the orbital in the presence of the electron correlation effects. So in these water clusters, what's important is not correlation to high order. It's allowing the orbitals to relax to the presence of the second order correlation effects. We're going to see later for C60, this is a little bit different. C60 is a much more highly correlated system. And to get quantitative results there, you need methods that include this orbital relaxation as well as high order correlation effects. Okay. So I've presented ab initio results here. And much of the work we've been doing in recent years is developing one-electron models to describe electrons interacting with water and other systems. And what prompted us to spend so much time figuring out how to do accurate ab initio calculations on these cavity-bound species is to make certain we had good numbers to compare the model potential results. I'm not going to go into the details of the model potentials, but I'm just going to show some results. So here's a water 24 cluster. This actual arrangement was first studied by Head Gordon and John Herbert. This doesn't bind the electron in the Hartree-Fock. But if you correlate it, it's almost bound 1 electron volt. So these are amazing systems. You can have no binding Hartree-Fock, but the exact solution will give a binding as much as 1 eV. These are sub-clusters cut out of this so that we maintain symmetry. Okay, so And this is just the electron density showing the 70% contour surface. Whoops. I think we got disconnected here. Probably don't even need it. What I'm showing you, there are 3 sets of results. These 2 are particularly important. One is the Green's function of calculations, the ab initio Green's function right here. This is, and right next to it in yellow is our most recent polarization model. This is a 1-electron model, and for these systems where electron correlation is very important, it quantitatively reproduces the electron binding energy of all the clusters. This is an earlier model that's not doing as well. And what the problem was, in the early model, we allowed the electron to polarize the waters. We allowed the water-water induction to impact the binding of the electron, but we didn't do all that self-consistently. Now the entire problem is treated self-consistently, and it does much better. So the problem is, if you have a cavity, that electron induces dipoles on all the waters. So that's an unfavorable arrangement of the dipoles. So you need a consistent treatment to account for the fact it's unfavorable to get dipoles pointed in the same direction. And that's the difference between the 2 model potentials. Okay, so needless to say, with the model potential approaches, these calculations that with EOM coupled cluster takes a week of computer time, we're down to a fraction of a second, and we can reproduce the equation of motion results. Okay, so I'm going to move now from the water to C60. These anions I was showing you, these cavity-type anions, you could say are polarization-bound anions, where I'm using polarization in the sense of adding a term to the potential that really is accounting for both induction and dispersion effects. So any species that's sufficiently polarizable should support such bound anion states. I know that Bob and Vince have worked on this C60 system in the past. There's evidence and papers from Rydberg atom collisions, as well as from low-energy electron scattering, that C60 attaches zero-energy electrons. But various mechanisms have been invoked. One of the mechanisms is one of the valence states, but there's a distortion that lowers the symmetry. Some people have suggested a polarization-bound anion. So what I mean by polarization-bound anion would be an S state that has most of its charge distribution outside of the C60. This has never been identified in ab initio calculation. So now that we have the tools that we developed from the water work, we will take a look at this. But first I want to tell you a little bit how we got motivated by this. My colleague, Havoya Petek, who does the TiO2 work with whom we collaborated, also obtained STM images of C60 clusters on a copper surface. And here's the image of a single C60 on a copper cluster. And at a certain voltage, you get an image that looks like this, which he attributed to this polarization-bound anion. And here's the dimer. And you can see essentially a bonding and anti-bonding combination at different voltages. So he calls these supermolecule states. He can take any number of C60s and make the bonding and anti-bonding combinations of this. But this is on a copper surface. There's a significant interaction between the copper and the C60. There's going to be an image potential effect. The fact that you can see these on a metal surface doesn't tell you that they're going to be stable in the gas phase molecule. So that's what we took on as a challenge. Just to remind you a little bit about part of the electronic structure of C60, here's the highest occupied orbitals here. There's several bound anion states. This is why C60 has proven so popular in electronic materials. The ground state anion, which is T1U, these are theoretical numbers. Experimentally, the electron affinity is about 2.7 eV. So there are several bound valence states. That's not the species that we're talking about. We're asking, is sitting up here, is there an AG type state which is weakly bound? Okay. So we applied the equation motion coupled cluster to this. You need very big basis sets, both on the carbons, as well as to allow for the radio extent. We did that by adding a very large set of diffuse SPD functions at the center of the C60 cluster. These are probably, or just about the largest equation motion coupled cluster calculations that have been done. on any system. And we find with the largest basis sets that the S-type anion is bound by about 1/10 of an electron volt. Here's a picture of psi squared. That's actually for the singly occupied orbital. From the natural orbital, here's the psi squared r squared, because it probably makes a little bit more sense to look at the radial distribution function. So there's charge inside the C60, you have orthogonality at the surface, and then you have considerable electron density outside. And this is just the integrated probability. So about 9% of the electron density is inside the C60, the rest of it is outside. Okay, so you look at the natural orbitals, the occupation numbers of the natural orbitals, the so-called singly occupied orbitals about 0.98. There are several empty orbitals that have very low 0.05, 0.1 occupation. There are several filled orbitals that have, instead of 2, 1.99. Those fractional occupations, to some extent, are describing the dispersion. So the correlation effect here is excitation of the diffuse electron plus excitation of one or more of the valence electrons of the C60. Okay, so in this case, the equation of motion MP2 and the equation of motion coupled cluster give binding energies that differ by factors of 2 or 3. For the water is essentially identical. And I think that's because the C60 is a much more highly correlated system. The second order Green's function method gives much stronger binding here. And I think that's an artifact because that's a second order Green's function isn't allowing properly for the screening effects that would take place in a C60. So let's go back, and I know you can find pictures like this many places in the literature, but let's think about the interactions that play here. So all we've done is taken a point charge and bring a negative point charge in towards the C60, and we've calculated the electrostatic and the polarization potentials that result from that. So the electrostatic interaction is essentially negligible at long range, but it's quite attractive inside. And this has been actually left out as some model potentials, not all, but some model potentials that have been introduced in the literature. So if you take a graphene sheet and you do a distributed multiple analysis, the leading moment on every carbon would be a quadrupole. But if you curve the sheet, the leading moment on every carbon will be a dipole. And the positive end of the dipole points is into the interior of the C60. So there's a sizable attractive electrostatic potential inside the C60 due to all the dipoles pointing in. In addition, the polarization potential is attractive both inside and out. So if you put a charge right in the middle, that's not a dipole, it's sort of a breathing mode type polarization. It's a contraction or expansion of the entire electron distribution. And outside you have a dipole polarization. But that has been modeled incorrectly in a lot of papers in the literature, not by anyone in this room, by the way, but in some of the other papers where one tacks on an alpha over 2 out of the 4. So what this green line here is the alpha over 2 out of the 4, and this is the ab initio polarization potential. And it's drastically different. The reason is pretty clear. I have a picture later, but I can state it in words now. Much of the polarization of the C60 is charge flow. So you're moving electron density from one side of C60 to the other due to the presence of the electric field. That means if you have a point charge, you have to be very far away from the C60 to model that as alpha over 2 out of the 4. So there's a 1 over R6, there's a 1 over R8. These higher order terms in the polarization are important. And it's surprising how many models have appeared in the literature ignoring that. So armed with our ab initio polarization and our ab initio electrostatic, we can develop a model that reproduces this. Now I have to say there's a part that we had to fit, and that's this repulsive term right here. Now there are models introduced in the literature that are actually attractive at the C60 shell. The difference is we're introducing a pseudopotential where we want the pseudopotential to account for the orthogonality. This AG state has to be orthogonal to the inner AG states. And that makes the potential repulsive here. So here's our model potential. There's a 1 electron orbital for that. And that distribution is essentially identical from what we got from 1 week of computer time doing the equation of motion calculations. We're trying to develop more rigorous models for this right now, where we actually allow for the charge flow. So again, this is building on the work that we've done on water. I didn't show the model potentials there, but we have these point-inducible dipoles on every atom of water. In the C60, putting point-inducible dipoles on the carbons isn't going to cut it, because much of the polarization is charge moving from one side to the other. So we're actually developing a one-electron model now where we explicitly include for this so-called charge flow polarization. Okay, so that's still under the work. So how much time do I have? Another 12 minutes. Okay, so I'll just change gears, mention something that we've been dabbling with off and on for years, and then we'll probably stop a couple minutes early for questions. We've played for a long time with stabilization type methods to characterize mainly shape resonances and electron molecule scattering. And as I think we heard earlier, that N2 is probably the most widely studied case, and maybe CO2 is the most next. Although I have to think beryllium atom has to be somewhere in terms of the systems that one has characterized the temporary negative ion state. So we've been investigating some of the newer electronic structure methods, how well they do. So this is an equation of motion coupled cluster, the same method that we used to study that water and the C60. These are different eigenvalues as a function of scale parameters. So this is the scaling of the most diffuse pi star type functions in the basis set. And you can see this pronounced avoided crossing right in this region right here. So essentially in a diabatic picture, and this is I think well known to everyone here, you essentially have your discrete state, which is your resonance, and then this is your approximation to a continuum. You get an avoided crossing between that. And we and others, years and years ago, developed techniques of fitting this results with a proper analytic continuation procedure, and then finding the complex stationary points as the way of characterizing the real and imaginary parts of resonances. These methods work incredibly well on these high symmetry small systems. You get into these low symmetry cases, it's far less successful, as I think anyone here who's tried that has known. Okay, so let me show you some results here. So this is at the equilibrium geometry of N2. We get an energy of 2.6 eV, which is very close to experiment, and a width of 0.3 eV, which is very close to the values that are extracted from fitting experiment. Down here, I show a time-dependent DFT method using Hartree-Fock exchange. Now, this sounds very, very strange, but there was a paper published a while ago by Kieran Burke, and I think everyone here knows that Kieran's one of the pioneers in density functional theory, and he was studying bound anions and using time-dependent DFT type approaches. And what he pointed out is much of the problem would go away if you used Hartree-Fock orbitals rather than the DFT orbitals in the expression. So we're just borrowing his equations and extracting multiple roots. Now you might wonder how we're applying this excited state method to an anion. We're using this technique that's pretty well known in the community. We add an incredibly diffuse orbital to the problem. And then we're doing excitation energies of that. This is, I think this trick might even be in QChem, right? Yeah, I know John Stanton has used this in the past. So essentially any method that can calculate excited states, you can also go after anions by having this artificially incredibly diffuse thing as your starting ground state and then doing the excitation energies of that. Okay, so let me show, these are the lifetimes as a function of internuclear distance of the N2. The deviation of the lifetime from the EOM coupled cluster. So we're taking EOM coupled cluster as our benchmark. And if you do a standard time-dependent DFT with, let's say, a PBE functional, the lifetime has no resemblance to what you get from the equation of motion. If you make use of Karen Burke's idea of using the Hartree-Fock orbitals in the DFT, it's essentially right on top of the equation of motion coupled cluster. So this is showing that there are some methods in electronic structure codes that are computationally pretty fast that can be applied to characterizing these temporary anion states to pull up the real parts and the imaginary parts. Okay, so I think on that note, I will stop and not get and entertain any questions.
When you attempt to include correlation in your many-body method, you're probably using a Hartree-Fock virtual orbital, right? I mean, any many-body method will be with the particle states that come out of the
Yeah, so the equation, so let's take the equation of motion. We start that off with Hartree-Fock orbitals. But one includes very, very high order excitations that essentially can renormalize the orbitals.
Yeah, but what I'm asking is that those virtual orbitals are not the ones that really try to capture polarization.
I'm totally, that's the point we're trying to make. So if you're willing to put in all the configurations that renormalize that, as you do in equation of motion coupled cluster, you're fine. But what we've shown is even crude methods like MP2, if you re-optimize the orbitals, so now you get rid of this problem that the Hartree-Fock sync orbital is a continuum, they work reasonably well.
When we do our polarization calculation, if we use the Hartree-Fock virtual orbitals, we never converge. What we do is we take those Hartree-Fock orbitals, we diagonalize and have it go into a highly quantum charged ion. We get a transformation of those
Right.
because we bring that density way down into where you want polarization.
Well, again, I think these orbital optimized methods are doing that. I should point out, we've converged these results on the water clusters in the C60s, but we've had to put in many, many, many more configurations. If you think about a configuration expansion than you would have in your treatments.
When the simple methods fail, are you doing this in these very large basis sets that have a lot of diffuse functions?
Yeah.
Well, then if your reference orbital is a continuum orbital
Yeah.
rather than you'll never get it converged.
No. The Green's function methods and the equation of motion methods have no trouble. I plotted the orbitals. They are localized. So they're free of the fact that the Hartree-Fock orbitals are totally wrong. Maybe Anna wants to check in on that.
I want to comment here that the proper methods are relatively orbital intensity. When the equation of motion, when you deal with an attachment variant, you don't care about unstable line states. It's a method that's designed to tackle
Right.
correlation without relaxed states.
Right. But the second,
Very nice feature of this method, and you do not care what the virtual orbitals are.
I should point out, the sort of the simplest method that gets these right is this, not the C60, it has an error, but on the water clusters is the second order Green's function. But the key in the second order Green's function is the off-diagonal terms re-optimize the orbitals. If you don't have the off-diagonal terms, then the fact that Hartree-Fock is starting off as a continuum, you never recover in the Green's function method. But both the Green's function and the equation of motion have no trouble describing these states in the continuum.
I mean, all I'm saying is that from the get-go, transform your virtual orbitals into a representation that's much more compact. That's all I'm saying.
Yeah, so if we did that and we were using natural orbital techniques, we could truncate the size space that we're treating.
That's what I'm suggesting.
Right, I agree, but the results we do have, even though they're computationally pretty demanding, I'm pretty certain are close to converged.
Yeah, I have a question about the equation of common. In TDDFT, you can prove Coupon theorem in a very awkward way. If you consider CIS calculations to which you add diffuse orbitals, or Poisson calculations, decided state calculations of this sort, you can see that that what you will get from this calculation is exactly equal energy pair. So that's why if you do P with the standard distribution, that gives you exactly, when you use quantum multiples,
Right.
it gives you that result. So that's common. And the question is, so what code did you use for cluster calculation?
Yeah, so the coupled cluster was done with C4, John Stanton's code, and I think we had John mentioned in one of the earlier talks. Yeah, so we had to go in and make several changes to that, and John was incredibly helpful in doing that. It actually, for example, it wasn't running, this is real detail, but we needed to run these in parallel, and the way we were doing the EOM EA wasn't parallel. We had to make some changes for that. Yeah.
Let's take one
I
more
had
question.
a question about the C60 model potential. So if you make the potential deeply attractive at the carbon edge, you'll get bound AG,
Yeah, but there is...
which you'll then be orthogonal to.
Right, but you don't... So there's two approaches to pseudopotentials. One is that you go after a whole slew of states.
Right.
The other is that you add the repulsive term, which knocks out the inner states that you don't want. So you get a 3 EVSO binding of the lowest AG state in your potential. And then it's very attractive near the C60.
Right.
But I'm not certain that it's getting all the other bound valence anion states.
So, but
Right.
using a repulsive model.
In fact, there is no strongly bound AG state.
Oh, the 1s or something, right?
Yeah, but this is the potential that you generated for the n electron system for the n+1 electron coming in. You took your density from the n electron system,
Right.
and then you get a state which is bound AG, which is an n+1 electron state.
Right.
There is no AG n+1 electron system for C60.
But, I mean, in the Hartree-Fock picture, right, the same potential gives you the bound orbital, which is the continuum. But, no, so...
Right. So, but there's two approaches to the pseudopotential.
Right, exactly. So you can get a similar result by having a strongly attractive and orthogonality because you're orthogonal to bound state. The question I had, the comment I had was, if you make it the repulsive, I can imagine getting scattering states up above, they're trapped by the repulsive potential, which are totally unanticipated. That would be the one concern I have.
That's a concern. So we need a more rigorous way of generating this repulsive potential than what we've done so far. I agree.
Actually, they're physically very different from the real potential.
Well, okay, we should chat about that.
Yeah, okay. I think we should cut it short. We'll get to our last talk. Jonathan Tennyson. Thanks very much, Dan. Jonathan Tennyson's last talk this morning found in continuum states in electron-molecule collisions using
I think you can just toggle over